Welcome, future builders and innovators. Have you ever paused to wonder how those towering bridges manage to be perfectly aligned? Or maybe how engineers know exactly when a massive dam is flexing under the immense pressure of water?
It's definitely not magic.
Right. It all begins with the foundational science of surveying. This isn't just about, drawing lines on a map.
No, it's much deeper. It's about understanding the very ground beneath our feet and how our incredible creations interact with it.
Our mission today, in this deep dive, is to embark on an essential journey through the fundamental principles of land surveying and linear measurements. Think of this as your essential toolkit, equipping you to translate complex designs from paper into the concrete reality of the built world.
Ensuring that everything you build stands exactly where and how it should. We're talking precision, we're talking safety, really the bedrock of civil engineering.
Absolutely. We're going to begin by clearly defining what surveying is and, crucially, why it forms such an indispensable foundation for civil engineers. We'll explore its various classifications and the core principles that guide every successful survey.
And then we'll dive into the truly practical side, dissecting linear measurements, the specific tools involved, understanding the common errors we encounter, and most importantly, how to correct them.
Even when faced with those tricky obstacles in the field.
Especially then. This isn't just theory, it's the practical wisdom that underpins your entire engineering career, packed with surprising insights and, well, practical knowledge that will literally change how you see the ground beneath your feet.
So let's unpack this. We're starting with Chapter 1, Introduction to Land Surveying. In this first section, we'll establish a solid understanding of what surveying entails, its vital role in every phase of a civil engineering project, how we categorize it, and the fundamental rules that ensure accuracy.
What's fascinating here is that surveying is fundamentally the technology of making scientific measurements on the Earth's surface. The desirable end products are things like accurate maps and a precise understanding of the Earth's true figure or shape.
And for civil engineers, this isn't just a preliminary step.
Oh, absolutely not. It's your initial canvas, your foundational data upon which every subsequent decision and design rests. Without it, you're essentially building blind. You wouldn't know where to start.
And it's not just one step in a project, is it? The material shows surveying is critical at 3 distinct stages, almost like a project's life cycle, from conception to long-term monitoring.
Exactly. The first stage is all about preparing maps and understanding the Earth's shape. Surveying is indispensable here because it creates those detailed maps of an area, capturing every natural and man-made feature, along with the precise topography of the ground.
So the hills, the valleys, existing roads, buildings, everything.
Everything. These maps are the civil design engineer's primary reference, their first look at the landscape. They inform every design drawing and calculation for everything from buildings, bridges, and highways to complex irrigation schemes, dams, reservoirs, and even underground tunnels. It's truly the initial blueprint.
The comprehensive overview that dictates what can be built and where.
Precisely.
So it's about seeing what's there before you even start to plan. You need that accurate spatial data to even begin dreaming up a design. Then, once the planning is done, surveying shifts gears into the next critical stage.
Yes. The second stage is setting out construction and development works. This is where the abstract designs move into the tangible world. Surveying ensures that these designs, once completed and perfected on paper, are accurately transferred to the ground with pinpoint precision.
The bridge from abstract plans to physical construction.
Exactly. This applies to laying out civil engineering projects like buildings, bridges, highways, and dams, but also to underground structures such as tunnels and pipelines, or even overhead systems like transmission lines. Precision here is absolutely paramount.
I can only imagine the consequences of getting it wrong.
Imagine the costly errors, the budget overruns, or even catastrophic failures if a bridge pier was just a few centimeters off its intended mark. Surveying prevents those catastrophic misalignments, saving time, money, and, frankly, lives.
And it doesn't stop there. Once construction starts, surveying continues to play a vital role, right? It's not just about getting the initial layout correct.
That brings us to the third, often overlooked but critically important stage, monitoring construction and deformations. Surveying isn't a one-and-done process. It's crucial for ongoing monitoring, quality control, and management throughout a project's life cycle and even long after completion. This ensures proper alignment during construction, for instance, checking the horizontality of floors in a high-rise building or maintaining the specific curvature of an arched dam.
It's the constant guardian ensuring your structure behaves as designed.
You got it.
That sounds like where things get really interesting and, frankly, where safety comes in. Monitoring for deformations, that's a big deal. What happens if a structure starts to move in unexpected ways?
It is a very big deal. Surveying measures the deformation and displacement of both existing structures and ground movements. Think about the settlement or tilting of buildings over time, or the subtle movements of natural or cut slopes, which can indicate a potential landslide.
So it gives early warnings.
Exactly.
Yeah.
This is where lives and property are directly protected because these measurements give us those early warnings of potential failures. Let me give you a powerful illustration. The concrete arch Victoria Dam in Sri Lanka.
Okay.
This dam, being a massive structure, naturally deforms with changing water loads it flexes.
Right, the pressure changes.
Correct. To monitor this, target prisms are fixed to the dam's face and along its crest. Then, total stations think of them as highly advanced electronic transits combined with an electronic distance measurement device, an EDM.
Measuring angles and distances together.
Precisely. Often up to 3 kilometers, with incredible angular precision, sometimes down to 1 arcsecond. These total stations are used from fixed reference points to regularly monitor the positions of those prisms.
So you're constantly checking tiny movements.
Yes. By analyzing the measured distances, engineers can visualize the dam's movement. If an unacceptable movement occurs, say during reservoir filling, operations are halted immediately to investigate.
Wow. The potential for catastrophic failure if ignored.
It highlights the stakes involved. It really does.
Wow, that's incredibly complex. How do they even install these prisms on a double-curved dam face, possibly in rainy or difficult weather? That sounds like a monumental task in itself.
It's a significant engineering challenge.
Yeah.
The team had to develop a special gantry-like system suspended from a crane to safely reach the dam wall, even at its most concave sections, just to install these instruments.
Yeah.
They installed 72 prisms across the dam wall and crest, and another 72 on the banks. And modern systems, like Trimble S9 total stations, automatically collect data every 3 hours. Consistent, reliable information.
That level of detail in monitoring is what prevents disasters. It's a testament to the precision and continuous oversight this surveying provides. But I wonder, for someone who might be newer to the field, what's a common misconception about surveying that a story like the dam example immediately shatters for them?
That's a great question. I think for me, it shatters the idea that surveying is just a one-and-done job at the beginning of a project. The Victoria Dam example shows it's an ongoing, life-saving process that continues throughout a structure's lifespan, constantly vigilant. It's not just about placing concrete, it's about managing it over time.
Exactly. It's about managing the living structure and its interaction with its environment.
That's a fantastic, real-world example of why this is so important. Now let's talk about classification. Surveying isn't just one big thing, is it? There are different types based on what you're trying to achieve and the scale of your project. Precisely. The primary classification divides surveying into 2 main categories, plane surveying and geodetic surveying.
Okay.
For smaller areas, we use plane surveying. Here, we neglect the Earth's curvature, treating the surface as a flat plane and any triangles formed on it as simple plane triangles.
So for a small building site, we can essentially assume the Earth looks flat.
Essentially, yes. The errors introduced by neglecting curvature over short distances are negligible. It simplifies the calculations for localized projects.
Makes sense. But for larger areas.
Then we enter the realm of geodetic surveying. Here, the spherical shape of the Earth is accounted for using spherical triangles. These surveys are typically far more precise and cover extensive regions like entire countries or continents. This is the realm of national mapping agencies, for example.
Got it. Beyond that, I see surveying can also be classified by the specific field of survey.
Indeed. Under land surveying, we have topographical surveys, which are essential for civil engineering projects. These map natural and man-made features like contours, streams, roads, buildings, forests, giving you that complete picture of the terrain. Then there are cadastral surveys focused on fixing boundaries and property demarcation. These often require licensed surveyors due to their legal implications.
Right. Property lines are serious business.
Very serious. And finally, city surveys, which are crucial for urban planning, management, and development, covering things like street construction and buried or overhead services, effectively mapping the pulse of an urban environment.
Okay. And you also mentioned classification by instruments.
Yes, though modern syllabi have evolved considerably. For this deep dive, we'll get into chain surveying in our next chapter. You'll cover leveling and theodolite surveying in later modules. It's worth noting that methods like compass surveying and plane tabling, while historically significant, are largely considered obsolete for modern precise work. They've been replaced by more advanced technologies.
And our main focus is clearly engineering surveying, right? This is the one most relevant to our listeners.
Absolutely. That's directly related to civil engineering works, which is our primary concern here. It's the application of all these principles and classifications to the built environment.
Okay, let's talk about the how of accuracy. What are the core principles that underpin all this precise work? These aren't just suggestions, they're fundamental rules, aren't they?
They are indeed fundamental. The principles of surveying are paramount, guiding how we achieve accuracy and avoid error propagation. There are two main ones. The first, and arguably most important, is working from the whole to the part.
That sounds counterintuitive at first glance. You start with the big picture and then zoom in. Why not just measure everything as you go?
That's the key insight. The core idea is to begin with a precise control survey to establish widely distributed control points with very high accuracy across the entire area. Think of this as laying down a super accurate, unshakable skeleton for your project.
A framework.
Exactly, a framework. Then and only then do you conduct subsidiary detail surveying within this highly accurate framework, maybe at a slightly lower level of precision. This creates a robust backbone for your entire survey.
Right.
For horizontal control, this establishes easting and northing coordinates, or longitude and latitude. Historically, this was done by triangulation, but now precise traversing with EDM is common. For vertical control, we establish altitude, the z-coordinate, by running a closed line of levels through all control points.
So you're setting up a super accurate grid first, a network of highly reliable reference points, and then filling in the details within that grid. What kind of instruments are we talking about for these control surveys?
For horizontal control, total stations are incredibly versatile. They combine EDM for distances, often up to 3 kilometers, with electronic circles for measuring angles with precision down to 1 arcsecond.
Wow.
Optical theodolites, like the Wild T1 with 6 arcsecond accuracy, paired with EDM or even steel tapes are also used, though less common now. For vertical control, accurate level instruments are essential.
And how does this look in practice, say, for a big housing development?
For large sites like dams or housing schemes, a closed traverse typically begins at a known benchmark, or BM that's a permanent, precisely located reference point with a known elevation, and it returns to it, establishing all your control points along the way.
Closing the loop.
Exactly. For long, narrow sites like highways or pipelines, BMs might be established at intervals, say every 5 kilometers, and traverses are run between them.
But even with all that precision, measurements aren't always perfect, are they? There must be some error, some slight deviation when you try to close that loop.
You're absolutely right. Due to unavoidable errors, traverses don't close perfectly. We call this misclosure. You might have a small angular misclosure or a linear error.
Okay.
This misclosure must be within permissible limits, which depend on the project's required accuracy. If it is, then corrections are systematically distributed, kind of spread out proportionally to the angles or length. This adjusts the coordinates easting, northing, and altitude to achieve a mathematically perfect closure.
So you adjust the skeleton to make it perfectly fit.
That's a good way to put it. This systematic adjustment is vital for the overall accuracy of your entire framework. Once that precise control framework, with its adjusted coordinates, is established, then you move to the subsidiary detail surveys.
Filling in the gaps.
Right. This is where you fill in all the specific features and details, measured with reference to those highly accurate control points. This approach prevents the propagation and accumulation of errors. Any small error in a detail measurement is localized and doesn't snowball across the entire project.
That makes sense.
Total stations are great for this, quickly capturing all 3 coordinates of detail points around each control station. And if a subregion is hard to cover, you can establish additional subcontrol stations from your existing control points, always tying back to that robust main framework.
So whole to the part is the golden rule. But what if you're working on an incredibly tight timeline and the client is pushing to start detail work immediately? How do you, as the lead engineer, articulate the absolute necessity of whole to the part and the risks of skipping it?
That's a very common real-world pressure. You would have to explain very clearly that trying to build from part to the whole Surveying small areas independently and then trying to stitch them together leads to significant error propagation and accumulation.
It just doesn't fit together later.
Exactly. What might seem like a small shortcut early on becomes a colossal and costly problem later. Imagine trying to piece together a massive jigsaw puzzle where each piece was measured independently and slightly incorrectly. The whole thing just wouldn't fit. The small, localized errors would magnify, leading to large cumulative errors, distorted maps, and ultimately an inaccurate structure. Redesigns, potentially demolition, massive financial penalties, not to mention serious safety risks. Investing the time in that accurate, whole-to-the-part control framework up front saves vastly more time and money in the long run. It's non-negotiable for quality work.
That's a powerful argument for doing it right the first time. So that's the first principle. What's the second?
The second principle is to fix a new station by at least 2 independent processes. This principle is all about checking your survey work and building redundancy into your data collection.
Like measuring something 2 different ways.
Precisely. It emphasizes collecting redundant data, which allows you to identify and rectify errors. If you have 2 different ways to determine a point's position, maybe angles from 2 points, or a distance and an angle from another, you can cross-verify your measurements and have much greater confidence in your results. It's your built-in quality control system.
Now that we have the principles, let's nail down some of the language of the field. What are some common definitions civil engineers need to know in surveying? Every discipline has its jargon, and surveying is no different.
Absolutely. Starting with survey stations. These are critical points marked on the ground, usually with pegs or nails, that serve as primary reference points for all your measurements.
The anchors of your survey.
Exactly. Connecting these stations are survey lines, which form the framework of your survey. Then we have offsets, which are perpendicular distances measured from a survey line to a specific detail point, like the corner of a building or a tree.
These should be short.
Ideally, yes. They're typically measured with a linen tape and preferably kept short, say 10 meters or less, to maintain accuracy and prevent large errors introduced by slight angular inaccuracies in setting out the perpendicular.
Got it. And what about the direction of a line? That seems fundamental.
That's where the bearing of a line comes in. It's its direction relative to a given meridian. And there are 3 types of meridians we need to understand. The true meridian is a great circle passing through the Earth's rotation axis, the true north and south poles, and the observer's location. It defines the precise true north-south direction and is established by astronomical observations. The true bearing is the horizontal angle measured from this meridian.
So based on the Earth's actual rotation.
Correct. Then there's the magnetic meridian, which is the direction of freely suspended magnetic needle points. This is influenced by the Earth's magnetic field, which, as you know, fluctuates and isn't perfectly aligned with the rotational axis.
So the magnetic north isn't quite true north. That's an important distinction.
Exactly. The difference between them is the magnetic declination, which is the horizontal angle between the true and magnetic meridians. And while it might seem like a small detail in places like Sri Lanka, it's only about 4 to 5 degrees. Understanding this difference is critical.
Why is it so critical?
Well, imagine trying to use an old map based on magnetic north from decades ago. Magnetic declination changes over time and varies geographically. If you ignore it, that old map might lead you miles off course, or a structure built based on magnetic north could be significantly misaligned with true north today. These seemingly minor natural variations can have colossal, long-term engineering consequences.
Wow, so you always need to know which meridian you're working with.
Always. Lastly, an arbitrary meridian is just any convenient direction you pick for a purely local project, perhaps pointing towards a prominent landmark. But its use is discouraged for maps that need to integrate with national grids because it's hard to reorient them accurately later.
That makes perfect sense. You want something universally recognized and unchanging like true north if possible. And speaking of maps, scale is obviously crucial for translating the real world onto paper.
Yes, scale is fundamental for plotting and interpreting maps, defining the relationship between map distances and ground distances. We primarily use 3 types. Ratio, like 1.500, meaning 1 unit on the map equals 5,000 units on the ground. Equivalence, such as 1 centimeter equals 75 meters. And graphical.
Which is the line drawn on the map.
Right, a line with marked distances. And the graphical scale has a significant advantage, and this is a key insight. It remains valid even if the map is enlarged or contracted, say, through photocopying or digital resizing.
Ah, because the line shrinks or grows with the map.
Exactly. The ratio and equivalent scales become incorrect if the physical size of the map changes, but the graphical scale stays true. Without that graphical scale, engineers could easily miscalculate distances if the map's reproduction changed its size, leading to potentially costly errors. It's your silent guardian against scaling errors.
That's a super helpful detail. It sounds like a simple thing, but it prevents a lot of misinterpretation. Let's move on to systems of surveying. How are these points actually located in the field using different geometric approaches?
There are generally three main ways to fix a point C relative to a known line AB. First, triangulation. Historically, this involved measuring only angles from points A and B to the new point C. Knowing the baseline length AB and the two angles allowed you to calculate C's position. This was particularly useful in difficult terrain where measuring distances was hard.
Like mountains.
Exactly. Second, we have trilateration. This is, in a way, the opposite. It involves only linear measurements. You measure the distances AC and BC, and knowing AB, you can fix C's position, provided AC plus BC is greater than AB. This method is used in basic chain surveying.
And then there's traverse surveying, which combines both angles and distances. That sounds like a powerful technique.
That's right. A traverse survey involves a connected series of lines, or traverse legs, joining points called traverse stations. Both angular and linear measurements are taken along these legs. Traverses can be closed traverses, which start and end at the same station, or run between two known stations, like benchmarks.
The loop we talked about earlier.
Exactly. This setup is critical because it allows for robust error checking and adjustment, creating that self-correcting loop. In contrast, an open traverse neither returns to its start nor connects two known stations.
There's no easy way to check for errors.
Right. They have no direct checks on measurements and are generally used for preliminary surveys or specific linear works like a single pipeline or utility run where an exact closed loop isn't feasible or necessary.
Knowing how to check for errors leads us right into our next big topic, the reliability of a survey. Because no measurement is truly perfect, right? Even with the best equipment and intentions, there's always a degree of uncertainty.
Indeed. It's critical for engineers and surveyors to understand error because recognizing it is the first step to managing it. We need to differentiate between accuracy and precision.
Okay, what's the difference there?
Accuracy is how close a measurement is to its, well, unknowable true value. Think of it as hitting the bullseye on a target. Precision, on the other hand, is the degree of agreement among repeated measurements of the same quantity. This is about how tightly grouped your shots are, even if they're consistently off the bullseye.
So you could be very precise, but not very accurate.
Exactly. If your instrument has a systematic error, like a tape that's consistently too short, you might get very repeatable, precise measurements, but they'll all be inaccurate, consistently wrong in the same way. High precision doesn't guarantee high accuracy.
So if we can't know the true value, what do we aim for? What's our best guess?
We aim for the most probable value, MPV. Since a true value is never precisely known, the arithmetic mean, the average of a set of precise measurements, is considered the MPV. It's the best statistical estimate we can make based on our observations.
Okay. And when it comes to the errors themselves, how do we classify them?
We classify them into three critical types. First, blunders or mistakes, also known as gross errors.
These sound like the big avoidable ones, the oops moments.
They are. They're typically caused by a lack of concentration, a definite misreading, or misbooking. Their impact is large and serious. Examples include completely missing a whole chain length in your count,
Oh dear.
reading 194 degrees on a theodolite instead of 195, or, and I've seen this happen, holding a leveling staff completely upside down.
Really? Upside down.
It sounds basic, but fatigue or distraction can lead to it. That's why cross-checking and having robust field procedures are so vital. These blunders must be identified and eliminated from datasets because they significantly distort results. They usually stick out like a sore thumb if you review your data carefully.
Okay, so blunders are human error, often due to lapses in attention. What's next?
Next are systematic errors. These follow a definite mathematical or physical law and can be constant or variable. They arise from natural conditions, like temperature changes affecting a steel tape's length or atmospheric refraction bending light rays, or from instrument or methodology flaws, such as a zero error in an instrument calibration, or using that measuring tape that is consistently too long or too short.
So these introduce a consistent bias across all your readings. They always push the measurement in one direction.
Exactly. They're insidious because they aren't immediately obvious like a blunder. The good news is that if the governing law is known, these errors can often be eliminated or reduced by applying relevant mathematical corrections. If you know your chain is 30.02 meters instead of 30.0, you can calculate and apply a correction to all measurements made with it.
Okay, so you can account for those. What's the third type?
Finally, we have random accidental errors. These are the errors that remain after blunders and systematic errors have been removed or accounted for. They are generally small, can be positive or negative, and are frankly unavoidable.
Why unavoidable?
They arise from inherent imperfections in instruments, the observer's own physiological limitations, like slight variations in judging alignment or reading a scale, or constantly changing environmental conditions like wind vibrations, or the shimmering effect of heat haze on a hot day.
So these are the noise you can't entirely get rid of, the inherent uncertainty in even the best measurements. It sounds like measuring isn't just about reading numbers, it's about a constant battle against human limitations, instrument quirks, and the unpredictable world itself. It's almost humbling.
Precisely. You can't eliminate them entirely, but their effects are minimized through careful procedures and statistical principles, often referred to as the theory of errors. Understanding these three types of blunders, systematic and random, allows engineers to manage the reliability of their survey data effectively.
And the level of accuracy required varies, right? You don't need the same precision for every single project.
Yeah.
That's absolutely right. The required accuracy is often defined by the intended scale of the final map or plan. For instance, if you can only plot something to within, say, 0.25 millimeters on paper, then for a 1.1000 scale plan, your field measurements need to be accurate to 0.25 meters on the ground. Anything more precise might be lost in the plotting.
But it's not just about the map scale.
No, it's also governed by specific engineering tolerances needed for structural integrity. How precisely does that beam need to fit? And sometimes by legal standards, especially for property boundaries, where even a few centimeters can have significant legal and financial implications.
Here's where it gets really interesting, connecting all these measurements to a global context. Coordinates on the Earth's surface. How do we pinpoint an exact location with absolute certainty anywhere on the planet?
Any location on Earth is fundamentally defined by three coordinates: longitude, latitude, and altitude. Longitude and latitude use the Earth's natural reference axis. The equator is a great circle perpendicular to Earth's rotation axis. The prime meridian is the true meridian passing through Greenwich, UK, chosen historically as the 0-degree reference. The origin of this system is where these two intersect a theoretical point in the Atlantic Ocean.
Right, latitude and longitude from geography class.
Exactly. Longitude is the angle measured east or west from the prime meridian along the equator, from 0 degrees to 180 degrees. All points on a given meridian line running pole to pole share the same longitude. Latitude is the vertical angle measured north or south from the equator, from 0 degrees at the equator to 90 degrees at the poles. Parallels of latitude are small circles parallel to the equator.
And then there's height, which is equally important in civil engineering. We don't just build on a flat map.
That's altitude. This is the height above or below a reference datum surface. Typically, this datum is mean sea level, MSL, which is the average level of the sea surface over a long period, like 19 years or more, to smooth out tides and variations. This provides a consistent global reference for elevation.
So everything relates back to sea level.
For large-scale mapping and many projects, yes. However, for local engineering projects, coordinates might be referred to as eastings and northings relative to a local assumed datum plane. This simplifies calculations because you don't need to constantly account for Earth's curvature on that smaller scale, making site-specific planning much more manageable.
Fantastic. That sets the stage perfectly for the theory. Now let's roll up our sleeves and get into the nitty-gritty, the hands-on aspect, with Chapter 2, Linear Measurements and Chain Surveying. Here, we'll explore the fundamental techniques for measuring distances, the essential tools of the trade, how to execute a survey, and critically, how to identify and correct for all those pesky errors we just discussed.
Right. And before we jump into the instruments, it's important to acknowledge the enduring value of basic surveying techniques. In our modern era, with photogrammetry, electronic equipment, satellite surveying rapidly advancing, you might wonder if basic techniques like chain surveying are still relevant.
That's a great question. You'd think everything would be automated now. Lasers and GPS doing all the heavy lifting. Why bother with chains and tapes?
Well, what's fascinating is that for small areas, these basic surveying techniques are often still the most economical and convenient option. More importantly, they provide essential, fundamental knowledge for any engineer.
How so?
They give you a deep, intuitive understanding of measurement principles, error sources, and geometric control that even the most advanced tools rely upon. In chain surveying specifically, you're primarily making only linear measurements, no complex angular measurements. And for very small areas, you can still adhere to the whole to the part principle, maybe by setting out a baseline and two main
So
triangles.
she teaches the fundamentals.
Exactly. It's a fundamental understanding of how to measure the ground directly, something every engineer should grasp. Even if they later operate a sophisticated total station or a drone, it builds that foundational intuition.
So let's talk about the toolkit for this. What instruments do you use for chaining and chain surveying? What does a surveyor's bag look like in the field for this kind of work?
Okay, your basic toolkit starts with the steel chain. These are typically 30 meters long, made of robust steel wire links. They usually have brass or plastic tags at meter intervals, maybe every 5 links per meter. They're incredibly durable for rugged use in various terrains.
Maybe not the most precise.
Correct. For higher precision, we use steel tapes. These are flexible steel strips, often 30 or 50 meters long, usually graduated down to millimeters. There are also plastic-coated or fiberglass tapes. They're lighter and resistant to water, but generally less precise and more prone to stretching than steel.
And what about for shorter measurements, like those offsets to a building wall or a tree? You wouldn't use a 30-meter scale tape for that.
No, usually not. For those, we use linen tapes. These are essentially reinforced cloth strips, sometimes with fine brass wires woven in to reduce stretching. They come in various lengths, maybe 20 to 50 meters, but they're primarily used for measuring the shorter perpendicular offsets where high precision isn't as critical as for the main survey lines.
Okay. And marking points.
To mark points during the chaining process, especially the end of each chain length, you use arrows. These are typically 40-centimeter steel wires pointed at one end, with a loop at the other where you can tie a piece of colored cloth or flagging to make them easy to spot in the grass.
Right. And for the main survey stations.
To establish your survey stations, the key control points, you need a mallet and pegs. A wooden hammer, the mallet, is used to drive wooden pegs into the ground. These can be small, square pegs for temporary points or larger, more substantial ones for main stations. For really crucial stations that need to last, pegs might even be set in concrete.
And to keep your lines straight over long distances, you need something visual, right? Something to aim for.
Absolutely. That's where ranging poles come in. These are typically 2-meter poles, maybe wooden or aluminum, of about 25 millimeters in diameter, usually with a pointed iron shoe to stick in the ground. They're painted in alternating bands of bright colors like red and white or black and white for high visibility over distance. They're essential for aligning long survey lines.
Okay. And setting out right angles. You mentioned offsets need to be perpendicular.
Yes. For setting out those perpendiculars accurately on the ground, we use specialized instruments like the cross staff or the optical square. An optical square is particularly neat. It uses internal mirrors or prisms. Prisms are more robust to allow you to sight along your main chain line and simultaneously see an object that is exactly 90 degrees off that line.
Clever.
Very. Finally, for measuring the inclination of a slope, which we'll need later when we talk about corrections, you'd use a clinometer. Each of these instruments, though seemingly simple, plays a crucial role in the accuracy of a chain survey. Mastering their use is fundamental.
Okay, we have our tools. Let's get into the actual field work. So with this essential toolkit now laid out, how do we translate theory and equipment into actual boots-on-the-ground action? Let's dive into the practical steps of chain survey field work. Where do you even begin when you arrive at a site?
The first practical step, and arguably one of the most important, is reconnaissance. This isn't just a casual stroll. It's an initial, thorough walkthrough of the entire area to be surveyed.
Scouting it out.
Exactly. You carefully examine the ground, identify principal features like existing buildings, roads, fences, significant terrain changes, streams, and so on. You're also determining the best positions for your control points, your survey stations, ensuring they have clear line of sight between them. Intervisibility is key.
And you make a sketch.
Yes. At the end of this reconnaissance, you prepare an index plan. This is also called a reference sketch, key plan, or sometimes a perspection diagram. It's a rough sketch showing the main ground features, the proposed layout of your survey lines connecting the stations, and some initial station numbering. This sketch guides your entire survey approach, preventing wasted effort later.
So you're sketching out your strategy before you even pick up a tape. What goes into selecting those key station locations once you've done your walkthrough? What makes a good spot?
Selection of stations is critical for efficiency and accuracy. First, you want to minimize the number of main survey lines needed to cover the area. Less lines means less measurement and fewer opportunities for error.
Makes sense.
You should establish a long baseline, usually running through the middle of the area as the main backbone of your survey. From this baseline, you build out a framework of triangles.
Triangles seem important.
They are the fundamental shape in chain surveying, and you want to ensure these are well-conditioned triangles. That means their internal angle should ideally be between 30 degrees and 150 degrees. Very sharp angles, less than 30, or very flat angles, over 150, lead to geometrically weak intersections when plotting, which magnifies errors.
Okay, so avoid skinny or squashed triangles. What else?
You need to include check lines. These are extra lines measured between stations, maybe across triangles, that aren't strictly necessary for plotting, but are used purely to verify the accuracy of your main measurements. Redundancy again.
Right, the second principle.
Exactly. Also, keep your offsets short, especially for important features like building corners, preferably under 10 meters if possible. Try to avoid obstacles that would block your view for ranging or make chaining difficult. Prefer level ground for your main lines if possible. And a practical tip: if you're surveying along a road, try to run your lines to one side to avoid interrupting traffic and for your own safety.
Good points. So once the stations are selected, mapped on your index plan, and strategically chosen, how do you physically mark them on the ground so you don't lose them?
For marking of stations, you use those wooden pegs we mentioned. For critical stations that you might need to find again later, or for long-term projects, you might use more permanent markers like cement pickets or even set the wooden peg in concrete.
And what if a peg gets disturbed or removed?
That's why you must create location sketches for each important control point. This is a simple sketch showing the station peg and measurements to nearby permanent features like the corner of a wall, a specific tree, a manhole cover. If the peg gets lost, that sketch allows you to precisely reestablish its position. It saved me more than once.
I bet. Okay, stations marked and referenced. Now the measuring.
Now the core work. Measurements or running the survey lines. You typically start from your baseline. You meticulously chain the line, measuring the length using your chain or tape, marking each chain length with arrows. And chainage, just to clarify, simply refers to the distance measured along a survey line from its starting point.
So chainage 125.5 means 125.5 meters along that specific line.
Exactly. As you chain along the line, you locate the details by taking those perpendicular offsets at the relevant chainages where features occur next to the line.
And you're breaking all this down immediately, right? You can't possibly rely on memory for all those numbers.
Absolutely not. Note-keeping is simultaneous with fieldwork, never deferred. You use standard booking procedures and a dedicated field book. There are a couple of common methods, like the center line method. Field book pages are usually formatted with columns for chainage, space for the offset distance and direction, left or right, and remarks. Often, small diagrams are sketched right in the field book to clarify complex shapes or features. Good note-keeping is as crucial as good measurement.
We've talked about scale before, but it's worth reiterating specifically for plotting these field notes into a tangible plan, isn't it? Because how you represent those ground distances on paper is everything.
Yes, scale in plotting is crucial. And again, you have the three types: equivalents like 1 centimeter at 75 meters, ratio like 1.5000, and graphical, the drawn line. The key takeaway here, particularly for you civil engineer students listening, is the practical advantage of the graphical scale.
Because it adjusts automatically if the map is copied or resized.
Exactly. It remains valid even if your plan is enlarged or contracted. Imagine the chaos if a map was resized digitally and suddenly your stated 1.1000 scale was actually 1.12000. On the printout, all your measurements taken off, that plan would be wrong. The graphical scale provides that unshakable visual reference, and you need to be comfortable converting between the types, understanding, for instance, that 1 centimeter equals 75 meters is the same as a 1.7500 ratio scale.
Okay, so we've done the field work, we've got our meticulous field book notes, maybe a bit muddy. Now we head back to the office. What about the chain survey office work? How do we turn those field notes and sketches into a professional, finished plan?
The office work transforms those raw field notes into a detailed, accurate, and legible plan. First, it's about plotting the framework. You typically draw the longest line, your baseline, first onto your drawing sheet. Then you carefully scale its total length and mark the positions of any subsidiary stations along it.
And then build the triangles.
Exactly. Using the measured side lengths of your triangles, you accurately construct them on the plan. A common way is using compasses. Set the compass to the scaled length of a side, draw an arc from one known station, Set it to the length of the other side, draw an arc from the other known station, and where the arcs intersect is your third station.
And you check this before adding details.
Critically important. You check these plotted triangles using your check lines measured in the field. Scale the check line distance on your drawing and see if it matches the measured length. If it doesn't fit within acceptable tolerance, something went wrong in the field or in your plotting, and you need to find the error before plotting any details.
Right. Fix the skeleton before adding the skin.
Precisely. Then, once the framework is verified, you move to plotting of details. You mark the changes along your plotted survey lines. Then, at each relevant chainage, you carefully scale off the offset lengths at precise right angles using a set square or protractor.
And connect the dots.
Yes. For features like fences or building outlines, it's best to join the plotted offset points as you go, building up the features piece by piece. Especially for dense detail, plotting and joining immediately helps avoid confusion.
What are the common pitfalls in plotting? I can imagine a lot of opportunities for mistakes here when you're dealing with lots of numbers and lines.
Oh, absolutely. You must guard against common plotting mistakes. Plotting an offset from the wrong chainage point on the survey line, plotting it on the wrong side, left instead of right, omitting offsets altogether, or mistakenly joining up the wrong offset points, creating distorted shapes. These can introduce significant errors into your final plan, misrepresenting the reality of the site.
So careful, methodical work is key in the office too.
Just as much as in the field. Once all the pencil work is done, verified, and accurate, you move to inking and finishing the plan. Traditionally, chain lines, station points, often marked with small circles or triangles, might be inked in a specific color like Prussian blue, while all other details, buildings, roads, contours, vegetation, are inked in black Indian ink.
And the final touches.
The finished plan must include essential elements. A north line, indicating orientation, usually true north, a clear heading or title, the scale, graphical is best, a legend explaining any symbols used, and usually the surveyor's name and the date of the survey. And of course, throughout both field notes and the final plan, you use appropriate, standardized conventional symbols to represent features like walls, fences, trees, marshland, etc., ensuring anyone can understand the map.
So we know errors are unavoidable. We briefly touched on them earlier, but let's delve deeper into errors in chaining and taping. How do they generally classify, and what are the specific culprits we need to watch out for during the measurement phase?
Right. Errors in chaining are broadly classified into two main types based on how they affect the total measured length: cumulative errors and compensating errors.
Okay.
Cumulative errors, which include most systematic errors and some types of blunders, accumulate progressively in one direction. This means the total measured distance will consistently be either greater or less than the actual length. The error just keeps building up with each measurement.
Like using a tape that's actually too short.
Exactly. If your 30-meter chain is actually only 29.8 meters long, every time you record 30 meters, you've only covered 29.8 meters of ground. So your recorded length is always longer than the true length. That's a positive cumulative error.
And compensating errors.
Those are mainly the random or accidental errors and maybe some minor blunders. They tend to cancel each other out over a long series of measurements because they're equally likely to be positive or negative.
Like slight inconsistencies in marking a point.
Exactly. Sometimes you might mark slightly ahead, sometimes slightly behind. Over many chain lengths, these small variations tend to average out, although you still strive to minimize them.
Okay, let's break down the specific causes of these errors. What are some of the major ones that every civil engineer needs to be actively aware of when chaining?
One of the most common and a perfect example of a cumulative error is an erroneous length of chain or tape. We just discussed this. If the chain is shorter than its nominal length, maybe due to wear or bent links, you record more than the ground length. That's a positive error in the recorded length, which means the correction you apply later will be negative. Conversely, if the chain is longer, maybe links stretched or kinks straightened out, you record less than the ground length, a negative error needing a positive correction.
So checking your tape length against a standard is crucial.
Absolutely. Before any precise work, another common issue is bad ranging. This is when you don't align the chain precisely along the straight line between the two survey stations you're measuring between.
So the chain follows a slightly crooked path.
Yes. This is always a cumulative positive error because any deviation from a perfectly straight line will always make the measured path slightly longer than the true straight line distance. This also seriously affects the accuracy of any offsets taken from that crooked line. Similarly, bad straightening, where the chain is allowed to lie curved on the ground instead of being pulled taut and straight, has a similar cumulative positive error effect.
Measuring on slopes seems like an obvious source of error, if not handled correctly. It can't be as simple as just laying the tape down the hill, can it?
Definitely not. Non-horizontality is a very common cumulative positive error. When you measure along a slope without either stepping the measurement horizontally,
What's that?
that's where you measure shorter horizontal segments, using a plumb bob to transfer the mark vertically down from the raised end of the tape to the ground mark for the next segment. If you don't step properly, or if you just measure along the ground surface on gentle slopes thinking it doesn't matter, you invariably measure a greater length than the actual horizontal distance.
Because the slope distance, hypotenuse, is always longer than the horizontal distance base.
Precisely. The error is always positive, making your measured length too long. Then there's sag, or catenary, another cumulative positive error. This happens when the chain or tape sags under its own weight between supports, maybe when measuring over undulating ground or across a small ditch, or even just if it's not pulled tight enough in the air.
The curve is longer than the straight line between the ends.
Right. The measured distance along the sagging tape between its ends will be greater than the true horizontal length between those endpoints. This error is minimized by using shorter measurement lengths, pulling the tape firmly to a standard tension, ideally, or providing intermediate supports along the tape's length if measuring in the air, catenary taping.
Okay, those are mostly cumulative, making the measurement too long. What about errors that might cancel out, the compensating ones you mentioned earlier?
Those would be things like careless holding and marking. This includes holding the chain handle slightly to one side of the station mark, fixing the marking arrows slightly off the true line, or slight inaccuracies when using a plumb bob. These are generally considered compensating errors because the errors are likely to be random, sometimes slightly to the left, sometimes slightly to the right, sometimes too short, sometimes too long, and thus can partially cancel each other out over many repetitions.
But you still try to be careful.
Of course. For high precision, you minimize every error source. Similarly, variation of pull tension, pulling the tape too much, stretching it slightly longer, or too little, allowing more sag, making it shorter effectively, compared to the standard tension it was calibrated at, can also be treated as a compensating error in ordinary work. Though ideally, you'd use a spring balance to maintain consistent standard tension for accurate surveying.
And temperature. You mentioned that affects steel tapes.
Yes, temperature variation. Steel tapes expand when heated and contract when cooled. This is technically a systematic error for any given measurement at a temperature different from standard, but over the course of a survey done over several hours or days with varying temperatures, the effect can be somewhat compensating. However, for accurate work, you measure the temperature and apply a specific correction. A positive correction is needed if the field temperature is higher than the tape's standard temperature, because the tape expanded, and a negative correction if it's colder, tape contracted.
So those are the inherent errors in measurement. But beyond those unavoidable imperfections, what about outright mistakes in chaining and taping? What are some common blunders that, with a bit of vigilance, can be completely avoided? These are the ones that can really ruin a survey.
Absolutely. Blunders are often much larger in magnitude than random or even systematic errors and must be avoided through careful procedures and checks. Some common ones include displacement of arrows. An arrow marking the end of a chain length might get knocked out of position and then carelessly replaced in the wrong spot.
How do you avoid that?
Always make a small scratch mark, or use a temporary peg at the exact point before removing the arrow for the next measurement. Miscounting of chain lengths is another potentially huge blunder. This can happen if the leader, person pulling the chain forward, drops an arrow and doesn't notice, or if the follower, person at the rear end, miscounts the arrows they collect, or if there's confusion during the handover of arrows, usually done every 10 chain lengths. This can throw off your total measurement by one or more full chain lengths.
That could be disastrous.
Again, the best practice is for both the leader and follower to independently keep count and to cross-check the tally, especially at the arrow handover.
I can imagine misreading the tape being a big one, too. You're out in the field, maybe tired, maybe the numbers are worn.
Absolutely. Reading 10 meters instead of 20, or maybe reading 6 instead of 9 if reading upside down, or misreading fractional marks like seeing 20.5 meters as 25 meters. These are classic. Always take a second look and have your partner check critical readings if possible. Closely related is erroneous booking. You read the tape correctly but write down the wrong number, maybe transposing digits like recording 5.79 as 5.97.
How to prevent that?
A good habit is for the person reading the tape to call out the number clearly and the person booking to repeat it back before writing it down. Verbal confirmation helps catch errors.
Good tip. Any other common mistakes?
Yes, a couple more. Reading the offset first and chainage later, it's easy to get confused and associate an offset measurement with the wrong chainage point along the line. Always ensure the chainage is noted clearly first, then the offset measured at that specific chainage. And finally, reading or booking right for left and vice versa when recording offsets. A directional mistake that's surprisingly easy to make if you're not consistently careful about your orientation relative to the direction of chaining. All of these are preventable with careful, methodical work and strict adherence to checking procedures.
Given all these potential errors and mistakes, systematic, random, and blunders, how do we get from our raw field measurements to the true values? What corrections to measured lengths do we need to apply to purify our field data and achieve the required accuracy?
This is where we systematically adjust our measured lengths to account for those known systematic errors we discussed. There are several standard corrections that are often applied, especially for precise work using steel tapes. First is the standardization correction.
That's for the tape not being exactly the right length.
Exactly. Tapes are calibrated against a standard reference, usually at a specific temperature and tension. If your tape deviates from its nominal length, I believe your 30-meter tape is actually 30.015 meters long under standard conditions, you apply a correction based on that deviation, delta L, and the nominal length L to every length measured. The correction is proportional to the measured length.
Okay. What about slopes?
The correction for slope is always subtractive. You've measured the distance along the slope, but you almost always need the horizontal distance for plotting or calculations. So using trigonometry, if you know the angle of the slope from a clinometer or Pythagoras, if you know the difference in elevation between the ends, you calculate the difference between the slope length and the horizontal length and subtract that difference from your measured slope distance.
Always subtractive for slope. Got it. Temperature.
Correction for temperature. This is applied based on the coefficient of thermal expansion, alpha, of the tape material, usually steel, and the difference between the average field temperature during measurement, Tm, and the tape's standard calibration temperature. The correction is alpha times the measured length times Tm2. It can be additive, if warmer than standard, or subtractive, is colder.
And the tension you pull the tape with matters too, right? Pulling harder stretches it.
Yes, exactly. The correction for pull or tension is applied if the actual pull you applied in the field differs from the tape's standard calibration pull. The correction depends on the difference in pull, TO, the measured length, L, the tape's cross-sectional area, A, and its Young's modulus, E, which measures its stiffness. More pull stretches it, positive correction. Less pull means less stretch or more sag, negative correction.
Young's modulus,
Okay.
bringing back physics.
It all connects. Then there's the correction for sag, catenary, which applies when the tape sags between supports. This correction is always negative because the curve of the sag is longer than the true horizontal chord distance between the supports. It's calculated based on the weight of the tape per unit length, the measured length, span between supports, and the applied pull. Higher tension reduces sag, hence reducing the correction.
Okay. Any others?
One more important one, especially if you're doing high precision work or connecting to a national mapping system, is the correction for altitude, or reduction to mean sea level. Distances measured on the Earth's curved surface at a certain altitude need to be reduced to their equivalent length on the MSL datum surface. Since the Earth's radius is smaller at MSL than at higher altitudes, this correction is typically negative for work conducted above MSL. It's usually a small correction, but necessary for geodetic accuracy.
So you might apply several of these corrections.
Yes, they are often applied sequentially. You might correct for standardization, then slope, then temperature, then pull, then sag, and finally reduce the resulting horizontal distance to MSL if needed.
It sounds like a lot of calculations and careful consideration for every single measurement, especially for high accuracy work. But what happens when you're out in the field and there's a big physical thing literally in your way? How do you deal with obstacles in chain surveying when you can't just measure straight through something?
Obstacles are a constant reality in surveying, and surveyors have developed ingenious geometric techniques to overcome them, essentially using geometry to measure indirectly what you can't measure directly. We can group these situations. First, consider obstacles to ranging, but not chaining.
meaning you can't see between the 2 points, but you could physically walk and measure the line if you knew where it was, like a hill or dense woods in between.
Exactly. If you can't see between your start point A and end point B, but intermediate points might be visible from the ends, you can use reciprocal ranging. Two surveyors, one near A and one near B, iteratively direct each other sideways until they're both perfectly aligned on the straight line AB. Then you can range the intermediate points along that now established line.
What if you can't even see intermediate points easily?
Then you might use the random line method. You set out a trial line, AD, from A that runs close to the true direction of B, but clear of the obstacle. You measure along this random line until you estimate your roughly opposite B. Then you measure the perpendicular distance, BC, from B to your random line AD. By measuring AC and BC, you can use Pythagoras to calculate the true length AB and trigonometry to find the angle at A needed to set out the true line AB if required.
Clever geometry. Okay, what if you can see across an obstacle, but you can't actually measure through it, like a pond or a river?
That's an obstacle to chaining, but not ranging. If it's a relatively small, chainable obstacle, like a small pond or a patch of thorny bushes you can walk around, you can often set out equal perpendiculars from your line before the obstacle, say BB, and after it, CC, creating a rectangle. You then measure the distance along the offset line, BC. Since BC equals BC, the distance across the obstacle, you've found your missing length.
Forming a rectangle around it.
Yes. Or you might use Pythagoras by setting out a right-angled triangle, where the distance across the obstacle is one side you need to calculate. For unchainable obstacles like wider rivers, you typically use geometry involving similar triangles or setting out parallel lines on either side of the river. By measuring angles and distances on your side, you can calculate the required distance across the river without ever having to cross it with a tape.
It's a wonderful application of basic geometry to solve real-world measurement problems.
It really is.
And the worst-case scenario. You can't see or chain through it, like a large building or a dense forest block sitting right on your survey line.
That's an obstacle to both ranging and chaining. Here you need methods to continue the line accurately on the far side. One common method uses right angles. Let's say your line ABC hits a building. At B and C, points before the building, you carefully set out equal perpendiculars, say BB1 and CC1, long enough to clear the building's width. You then extend the line B1C1 parallel to your original line, past the building. Then, from points D1 and E1 on this parallel line, you set out perpendiculars D1D and E1E of the same length, but in the reverse direction, back towards your original line's alignment. Points D and E are now back on the original line ABC extended.
Creating a parallel offset path around the obstacle.
Precisely. Alternatively, if setting out accurate right angles is difficult, you can use geometric constructions without right angles. For example, you can use properties of equilateral triangles or other specific angular relationships, like constructing congruent triangles, to extend the line past the obstacle using only distance measurements. These methods showcase the creative problem-solving often needed in surveying fieldwork.
It's all about finding an indirect way to get that direct measurement or alignment when the direct path is blocked. Finally, let's touch on ensuring those all-important right angles, which are crucial for offsets and some obstacle methods. Perpendiculars to chain lines. How do you get that 90-degree precision in layout in the field using basic tools?
Good question, as accuracy here is vital. When you need to drop a perpendicular from a point P to a line AB, say from a building corner P to your chain line AB, to measure an offset, you have a few options. For very short, non-critical offsets, experienced surveyors might use eye estimation, but that's not accurate.
Okay, what's better?
A common field method is tape swinging. Hold the zero end of the tape at the point P and swing the tape in an arc near the chain line. The shortest reading you observe on the tape as it touches the chain line marks the point, Q, where the perpendicular from P meets the line AB. The shortest distance is the perpendicular distance.
Finding the minimum distance by swinging an arc.
Exactly. For better accuracy, you can use geometric construction. With the tape end at P, strike an arc that cuts the chain line at 2 points, say X and Y. Find the exact midpoint Q between X and Y on the chain line. The line PQ is then perpendicular to AB.
Okay, that's dropping a perpendicular to the line.
Yeah.
What about setting out a line at 90 degrees from a specific point P on your chain line?
You can use instruments like the cross staff or optical square we mentioned earlier. They're specifically designed for this. But using just a tape, a very common method is applying Pythagoras' theorem with the classic 3-4-5 rule.
The right angle triangle sides.
Yes. From your point P on the chain line, measure 3 units, say 3 meters, along the chain line to point A. Then have one person hold the 0 end of the tape at P and another hold the 9-meter mark at A. 3 plus 4 plus 5. Oh, wait, let me rephrase. 3, 4, 5 rule with a longer tape. Hold 0 at A, 3-meter mark at P. Then find the 7-meter mark, 3 plus 4 is 7. Stretch the tape top from A at 0 and P at 3 meter, such that the 7-meter mark forms the third vertex Q. The angle at P in the triangle APQ will be 90 degrees because 32 plus 42 is 52, 9 plus 16, 25. So the line PQ is perpendicular to AP. You can use multiples like 6, 8, 10, or 9, 12, 15 for longer, more accurate perpendiculars.
A very practical use of basic math.
Extremely practical. Another geometric instruction is to mark points A and B on the chain line such that they are equidistant from your point P, say 5 meters each side. Then from A and B, swing arcs of equal radius, say 8 meters, with your tape. Where these two arcs intersect at point Q, the line PQ will be perfectly perpendicular to the chain line AB at point P. These techniques are fundamental tools for ensuring accurate layout in the field.
We've certainly journeyed through the intricate world of surveying fundamentals today, from defining its absolute purpose in civil engineering to mastering the nuances of linear measurements and, crucially, their essential corrections. And you've shown us how concepts like working from the whole to the part aren't just academic theories, but really practical rules that prevent potentially catastrophic errors on monumental projects, like that Victoria Dam example.
That's right. And understanding these basic principles, whether it's recognizing the different types of errors, knowing how to apply corrections, or skillfully navigating those inevitable obstacles in the field, it truly is the cornerstone of responsible and effective civil engineering practice.
It's clearly not just about reading a scale or punching numbers into a device.
Not at all. It's about developing that critical eye, that methodical approach that ensures everything from a small building foundation to a vast railway network is built on a foundation of unshakable accuracy. It provides the confidence to not just use the technology, but to truly understand the data it provides and its limitations.
So here's a final provocative thought for you, our listeners, to consider. In an age of increasingly sophisticated digital tools, GPS, laser scanning, drones, all these automated systems, how does a deep understanding of these basic, often manual surveying techniques we've discussed today continue to empower engineers? How does it help them to critically assess results, to innovate reliably, and ensure the fundamental integrity of the built world, rather than simply relying on technology as a black box without full comprehension? What new responsibilities and perhaps even opportunities does this foundational knowledge unlock in our rapidly evolving technological landscape?